So, in view of all that we have said in the foregoing sections, the many obstacles we appear to have surmounted, what cast the pall over our victory celebration? It is the curse of dimensionality, a malediction that has plagued the scientists from the earliest days. This is an extract from Richard Bellman's book, Adaptive Control Processes. This was published in 1961, and this is where the phrase, the curse of dimensionality, came from. Simply put, the number of samples needed to estimate an unknown function with a good level of accuracy grows exponentially, regarding the number of input variables in the model. Generalization is one of the key outcomes of a successful machine learning model. Essentially, how good is your model's ability to adapt to unseen data drawn from the same distributions as the one used to create the model? Let us break this down further. Imagine we want to design a model that tells us if a 5-year-old child is going to be above 180 centimeters when they are 21. In this model, there are only two binary variables that determine the height of the child in the future. If the father is above 180 centimeters, or if the mother is above 180 centimeters. This means there are 4 unique combinations of the variables in this example. We would need at least an example of each combination to generate a model that produces 100% accuracy in predicting people above 180 centimeters. Now, some people say this is overfitting, but for this example, we have all the combinations and we will not come across data we haven't seen before. Therefore, overfitting is not an issue in this case. Now, let's imagine there are 20 variables that determine if a child is going to be above 180 centimeters. The parents are smokers, the sex of the child has liver issues, if the mom had a high education level, all these other factors. If we only have 10,000 examples and each example is a unique combination of the variables we have, we still need around 1 million observations that are unique combinations of our variables to have a full representation of the model. This means there is a 95% chance of getting data we haven't seen before. There is no way we are going to have such a data set, and therefore we hope that with our training data we can get a generalized model that can predict a child's height. However, with the additional variables, it gets harder to get a generalized model, and this is because of data sparsity. Data sparsity simply means that we do not have enough data to capture the unique combinations of our variables. For example, let's take the father's height and assume there are 1,000 fathers who were below 180 centimeters when they were 21. In reality, the true probability of a child being above 180 centimeters at 21 when their father was below 180 centimeters is around 10%. However, our dataset contains only 1,000 observations of fathers who fit this description. This histogram shows what happens if we randomly drew 1,000 observations from the population for fathers that meet this criterion. There is a 15% chance that we would have drawn a sample of fathers that underestimated the probability of getting a child who would have been above 180 centimeters. Every time we add additional variables to our model, we are adding more conditions. So if we looked at the probability of a child being tall, given their father was below 180 centimeters, but their mother was above 180 centimeters, the true probability of that is 20%. However, we find that only 300 samples in our dataset match those criteria. We run the same exercise of trying to understand the odds of us drawing a sample that will underestimate the true probability of a child being above 180 centimeters when they are 21. The data looks noisier than what we had when the probability was only based on the dad's height. In this case, if we saw anything less than 18%, we class it as an underestimation of the true effect. And if that's the case, then there's a 20% chance that we could get data that underestimates the true effect. We have increased the sampling noise, and this means that we have also increased the chances of overfitting. Our model will not generalize to the rest of the unseen data because it has drawn decision boundaries based on the sampling noise and made wrong inferences, thus leading to overfitting. The example has shown that as we increase the number of variables, we increase the sampling noise and thus increase the chances of having an overfitted model. There are more problems with the curse of dimensionality. The curse of dimensionality ends up making all data points look similar. How? Let's take the GDP per capita and births per thousand women ages 15 to 19 from countries in West Africa and Western Europe. It is clear that there are two different clusters. Western Europe tends to have a smaller number of adolescent pregnancies and a higher amount of wealth per person, and it's the other way around for West African countries. I will use the Euclidean distance metric to measure the distance between each country, but first I need to normalize the data. GDP per capita and births for 1,000 women are on different scales. GDP per capita has a much larger scale than births per 1,000, and this means it will dominate our distance metric calculations between countries and make the births per 1,000 variable irrelevant. For example, if we calculated the distance between Spain and Portugal based on this metric, it would be around 130,000. What if the number of births from adolescent women went up from 2 to 6? The distance between both countries does not change. Even if 4 additional babies per 1,000 adolescent women is a pretty big jump in reality. What if Spanish citizens became $10,000 richer? The distance between both of them dropped to about 120,000. What if we scale transform our variables? When we replace the values with scale transformations, our distance metric is a bit more sensitive to changes in both variables. This is why we have to scale these variables. After that quick segue, we are back to our original question: what is the furthest country pair? And the furthest country pair is Monaco and Niger, with a pair distance of 5.8. Niger is one of the poorest countries in our dataset, whilst Monaco is the richest country in our dataset. The adolescent fertility rate between both countries is also wildly different. What is the closest country pair? It's Sweden and the Netherlands, with a pair distance of 0.02. They have very similar GDP per capita, and the adolescent fertility rate between both countries is practically the same. The ratio between the furthest and closest pairs can give you an indication of how dissimilar countries are given the variables we are observing in this space. The ratio between Monaco and Niger and Sweden and the Netherlands is 254. What happens when we increase the number of variables between countries? Here's a graph showing what happens to the ratio between the furthest country pair and the closest country pair as we increase the number of variables. You see that the ratio between the furthest and the closest countries reduces. As the dimensionality increases, the countries in our dataset start to look more alike. If all the countries are becoming similar, it becomes harder to draw sensible neighbors based on our dataset, and this is one of the difficulties with more variables. This was an attempt to explain why the curse of dimensionality can pose a problem in statistics.